Hey everybody, happy Friday. It's Mr. Betker back with another edition of our online physics sessions. Today is going to be a bit of a shorter one for a couple of reasons. First being that our last lesson got cut short, so I wasn't able to get to any of the examples from yesterday's lessons. So we'll just focus today on just doing the examples. There's only two of them, so it should be pretty brief. The other reason being, it's Friday. I thought maybe you would enjoy just having a little bit less of a length on today's lesson so that you could get to whatever it is that you want to do to keep yourselves busy and happy right now. Now, that being said, we're still going to do a problem of the day, also a pretty brief one, again, because we don't have a previous lesson's worth of examples to go from. So our problem of the day today is going to look as follows. Speaking of keeping yourselves busy and keeping yourselves happy, today is the International Day of Happiness. So that is the theme for our problem of the day. There you go. Now, for any Harry Potter fans, it's also Hufflepuff Pride Day today. So any Harry Potter fans, and what I have there is even less likely than being Harry Potter fans, any Hufflepuff fans. Today's your day. So have a good one. All right, so just for the question itself, predict the path of the red and the blue pieces. There's one key element here to this question, and that is going to be touched on when I go through the answer with you. But for right now, you've got your blue piece and your red piece, and that black piece is going to come and collide with them. We're kind of looking at collisions more often in this unit, and they're both going to behave a certain way after that collision. So take a shot at doing that. I'll give you a couple seconds here, and if you need a little bit more time, you can pause. I'll probably blab about Harry Potter a little bit more here. Who is anybody? Oh yeah, there's Cedric Diggory from Hufflepuff. I do remember that, the one notable Hufflepuff characters. If you guys remember any others, let me know because I can't remember any other ones. All right. There is what I have. Now you'll notice I'm going to flip kind of back and forth here. It's not, I didn't do it, super mathematically or anything like that. Just kind of eyeballed it, what it's going to look like. So if yours looks something like that, you are spot on. That's great. The key here is to note that both of these objects now were not moving before. So they weren't moving here now. And now I've set some sort of transfer of momentum from this piece to these two pieces. Now, based on my drawing here, this piece now stops moving, and these two are both the ones that are moving. So there's a transfer of momentum, okay? That transfer of momentum has to follow the law of conservation of momentum, meaning that the momentum before is going to be totally equal to the momentum after. So whatever momentum that black piece had in it before, it has now separately divided into the red and the blue pieces. So they'll be moving with less velocity, right? I mean, it all depends on what their mass is. But the key here also is that we have got angles, right? Neither of these are going perfectly in the X or Y directions. So that's one thing to keep in mind as we're moving forward, that you will, again, like we always do in this course, break things down into their X and Y components, okay? So now that we've done that, let's move on. We will go to, I just need to pull up the window here. We will go forward and do the two examples from the notes. Like I said, shouldn't take us too long, and then that'll be it for the day. You can go and enjoy the rest of your Friday. Got them here. I'm gonna put up the presentation window now, and we will get started. I hope that the notes yesterday were helpful for you. I did realize when I was watching it after that my voice got kind of quiet at certain parts. But like I said before, I will try to continue to get better at this. It's going to be a little bit of a learning curve for me. I might have to use a microphone and everything like that just to make sure that you can hear me properly. I also hope that it was useful. Please let me know if you are finding these useful, if you want me to keep doing them, because if not, I can just post the scanned notes and then there's no interaction at all. But I do think, at least if, from what I remember when I was in physics, I appreciated being able to follow along with somebody doing the work. So I do hope this is helping. I'll let you know when I'm planning to have a day that you can drop onto the Google Meets at a certain time and you can ask me questions in person. So I have had a few of you ask me questions over email, and it's a little bit more difficult to be able to get the points across over email, especially when we're typing stuff out. So let's go through example number one. We got our Hufflepuff colors for today. So a baseball with a mass of 0.15 kilograms has a velocity of 38 meters per second west as it approaches a batter. The bat applies a force causing the ball to move at 58 meters per second. So the bat is imposing a force onto that ball, causing it to move 58 meters per second. Now, if we have two things that we need to find here. We need to find the impulse acting on the ball by the bat, and we need to find if that contact time is 1.6 times 10 to the negative 3 seconds, what is the average force applied by the bat? So what I'm going to do here, I'm going to take another color, and I'm just going to, before I get started at all, I've got obviously east and west acting here, right? So I'm going to decide that my east direction here is going to be my positive, and my west direction here is going to be my negative. That is going to change things in terms of what our answer is going to look like, whether it's a positive or a negative. So let's start this problem by writing down all of the things that we know. Mass is equal to 0.15 kilograms. Okay, we have got V1 is equal to 38 meters per second west. And V2 is equal to 58 meters per second east. Now the question asks us to determine the impulse. So what is that impulse? And with impulse, if we can, we're going to try to include a direction. Okay, we're going to try to include a direction because it is a vector. So our formula that we're going to use is going to be I equals, now remember, I is equal to F times T, but we haven't been given F or T. What we have been given is M and V. And recall, maybe up here, that the momentum is equal to M times V, right? The momentum is equal to M times V. So we're going to use that because we know the relationship between I and momentum, between impulse and momentum, is that impulse is equal to the change in momentum. Now, if we think back to our notes from yesterday, we'll remember that if the mass doesn't change, that means that the velocity has to have changed, right? Obviously, this baseball is not losing any mass. So what that means then is that rather than having a change of mass, we have a change of velocity, okay? That's going back to right here, right? There's a possibility that it could be a change in mass, but in most cases, usually it's a change in the velocity, not a change in mass. So that's what we're going to use here. We're going to use the formula M times V2 minus V1. Okay? So using that, we'll have I, and what I'm going to do is I'm going to get rid of my vector arrows. I'm going to start using my scalars for this section right here. M is equal to 0.15. I keep writing that 5 first, but there we go. 0.15. Okay? V2, the final velocity is in the eastern direction, so that's going to be a positive 58. And then minus V1, which is in the west direction, the negative direction, so our value is going to be negative 38. And our final answer, if we do that, 58 plus 38 times 0.15 should give us 14. Should be 14.4, but we'll do 14 because we're using 2 sig figs, and it should be 14 Newton seconds. So the impulse is equal to 14 Newton seconds. Now that's a positive number, obviously, so our direction is going to be east. So there is our final answer right there. 14 Newton seconds east. Technically, you could argue that you could use the the unit of measurement kilogram times meters per second, because it is just a change in momentum. But when we're talking about impulse explicitly, I would like us to use Newton seconds, please. So that brings us to part B. If the contact time between them, so if delta T was equal to 1.6 times 10 to the negative 3, right, just a little bit of an instance of a second, what is the average force applied to that bat? Sorry, to the ball by the bat. This is pretty straightforward. We are now using a direct plug of the formula F times T is equal to impulse. So solving for F, we get I divided by T. So therefore, F is going to be equal to, we divide by T on both sides, and we get I, which is 14. I'm going to make sure that you're using 14.4. Okay, that's actually, I should have written that down. It's actually 14.4. I've said this before, don't use your sig fig answers in part B of a question because it will change your answer. You won't have it rounded to the same thing. 14.4 is quite a drastically different number when divided by 1.6 times 10 to the negative 3 for part B. So 14.4, okay, that's the one that we're actually using, divided by 1.6 times 10 to the negative 3. 1.6 times 10 to the negative 3. Now take a look at this, right? Like we could see if I do 14 divided by 1.6 times 10 to the negative 3, I get 8,750, okay? Whereas if I do 14.4 divided by 1.6 times 10 to the negative 3, I get 9,000, okay? That's a pretty drastically different number. 8,750 versus 9,000. So just be careful with that, okay? Because you're going to get like a pretty drastically different value. So F is going to be equal to 9,000 newtons, and it's also a positive number. So our direction for our force is going to be east. So there's question number 1. There's question number 1. That should give you some information to be able to work on. I think obviously a lot of you have probably already started doing the practice problems if you are interested in doing the work right now. But if you haven't, that should be able to help you get started. So example number 2, during a downpour, rain falls, I'm losing my notes here, rain falls at 15 meters per second down and hits the roof of a car. The mass of the rain is 0.6 kilograms per second. So every second we're having 0.6 kilograms happening, okay? Find the force exerted on the car by the rain. So 0.6 kilograms per second, it's kind of a weird, I really shouldn't have that written as mass. Basically what I should have is that we have 0.6 kilograms per second of rain falling. Okay, so let's break that down into its 2 little components that we have. What this is telling us, okay, 0.60 kilograms per second. What that's telling us is that we have a mass of 0.60 kilograms, and we have a time of 1 second. Okay, so every 1 second we have 0.6 kilograms of rain hitting the roof. Now, the rain is falling at, so the rain's initial velocity that it's falling with is 15, excuse me, 15 meters per second down. Okay, now I'm going to do something weird here that we have never really done before. Okay, the idea that an object hitting something and stopping is one that we've seen before. We've seen RC cars flying off of cliffs, right? We've seen pennies being dropped off of buildings. We never really ever think about V2 being 0. And that's because we need to calculate V2 the instant it hits the ground. But in an example like this, when we're looking at a conservation of momentum type problem, a transfer of momentum, or an impulse, okay, a change in momentum, we need to look at how the momentum of each object in the scenario changes. And in this case, the rain goes from moving to not moving, right? It goes from hitting so starting by falling 15 meters per second, but when it hits the roof of that car, it stops moving. So it's kind of counterintuitive compared to our kinematics minds that we've had so far. But V2 in this case is actually going to be 0, okay? So V2 is 0. And that's because we have a change in momentum going on, an initial momentum and a final momentum. All right, so let's make down positive and up negative because we're falling down, right? Everything's falling, all the rain is falling down. So it makes more sense to make that positive. Now, let's write out our formula that we're going to use. We're trying to find force, right? We're trying to find force. So force is a part of the impulse equation or the impulse formula, right? And remember that impulse is equal to the change in the momentum. So what we're going to end up with here, is if I replace both of these by their individual formulas we saw yesterday, we get F delta T is equal to the mass of the raindrop is not changing. So M, so that means that the velocity has to change, M times V2 minus V1. Okay, and now what we have is an interesting scenario, what ends up coming up here. I'm gonna plug in my time, my mass, and my velocities, okay? And we're gonna see something really interesting. So F is going to be equal to, well, let's say times 1, right? Times 1 is really not doing anything there, okay? It's equal to 0.6 times V2, which is 0, minus 15, right? Remember, it's down, so it's a positive, minus 15. So what we get is minus 15 times 0.6. Okay, minus 15 times 0.6 gives us negative 9 newtons. So our force is equal to negative 9. Now, this is interesting, right? Because we're getting a negative number, which means that it's going to be up. What we actually found here is we found the force exerted on the rain by the car, okay? Because in any scenario like this, we'll have a force acting on both of the objects. Remember Newton's third law, every action force has an equal and opposite reaction force. So what we end up with here is what we found is that there's 9 newtons of force up acting on the raindrop. So this is the force on the rain, exclamation mark for you because this is a big revelation, okay? We still use exclamation marks. And using Newton's third law, I can't even write this. Yeah, Newton's third law, we know that if the force acting on the rain is going to be upwards, right? The rain is not going to be having more force experience on it downwards, then we can deduce the fact that the force acting on the car is going to be 9 newtons down. And we should have it, I believe, unless I'm missing a part of the question. Oh, and I broke my whiteout yesterday by dropping it. It should be 9.0 newtons down. Okay, so that is our final answer. Kind of a strange little turn of events at the end there, finding the force acting up on it and then finding the force acting down on it. There's a couple different ways, like always, to look at these different problems. If you set this up differently, you ended up getting a positive. That's fine. Just make sure that you're make sure that you're being aware of the fact that the rain is going to have a force acting upwards on it, and the car is going to have a force acting downward on it. So, have a good rest of your day. If you have any questions about anything that we did today, just comment on the Google Classroom. On Monday, we'll pick up with conservation of momentum in one direction, okay? And then obviously, like we do in physics, we are going to move afterwards into two directions. Conservation of momentum in two directions, X's and Y's, like I know you guys love to do. So, like I said, have a good weekend. We will chat soon. I'll let you know about when we can discuss some problems or some questions that you might have on Google Meets. I will be posting on the Google Classroom very regularly. All right, take care.